Alright, Physics 12. We now get into a little bit of a section on focusing on equilibrium, and that involves a discussion today on torque. Okay, so when we talk about things in equilibrium, right, you might think about all the forces acting on a particular object, and if it's not moving, it's in equilibrium because the force acting on the right and acting on the left, pushing it together, it's like they're equal, so it's not moving, right? So you might think of, okay, that's something in equilibrium. Okay, so what we need to talk about more is other forces that could be acting that it appears as though an object is in equilibrium, but it's not, and that leads us to this aspect of torque. So let's get into that. All right, so as mentioned, if you were kind of looking at this diagram here, right, it has equal and opposing forces being applied to it, right? So I mean this force here, pushing here to the right, and then is equal to this one here pushing to the left. And then each of these that's forced at an angle has an equal and opposite force at the other angle. So you'd think, okay, well, that's not going to move because it's equal and opposite forces, and according to our laws of motion, then we'd be in equilibrium and not move. However, we need to also remember that we have the ability to be able to move through rotation. Okay, it's not just moving up, down, left, right, we can also be rotating. All right, so we have to consider that type of motion when we're considering whether an object is in equilibrium or not. Okay, so like I said, we've already kind of been considering objects as these point masses, and we observe the motion of the point in space. Right, so I mean, we just did a whole thing on two-dimensional collisions where it was this one object. It moved. It could move up and down. It can move left and right. But we didn't consider these masses or balls, let's say, spinning, right? We didn't interpret that. We just kind of did it as, okay, it's moving forwards and backwards and left and right, and that was it, okay? But obviously, real objects, right, if we consider that two-dimensional lab that we just did, if these were actual, like, billiard balls, of course, you can put a spin on a ball, right? And all of a sudden, that adds to, a type of force that's being, applied to that ball as well, right? So when we're working with large objects as opposed to just point masses, okay, motion can be divided into two types, and we can classify them as either translational motion and rotational motion. Okay, so here are some more key definitions. One is going to be the pivot point, and that pivot point is just the point around which a rotation occurs. All right. Then you've got your two types of motion that we just mentioned, right? Translational motion, which is the motion of the object as a whole caused by forces acting on the center of mass. Okay, so this is kind of what we've been dealing with so far. It's just kind of the object as a whole is moving, forwards, backwards, left, right kind of thing. Okay, but then we also have rotational motion, right, where we have angular motion around a pivot point caused by forces acting on a point other than the center of mass, right? So again, you can kind of think about, I guess in this case, like almost a door, right, where, you don't necessarily always press on the door in the center of its mass, you press on it on the side, and that kind of causes it to have some motion, right? It kind of starts to rotate, right? So I mean, with rotational motion, it's moving at an angle and around a particular pivot point. So in my example of the doors, it'd be like the hinges would be those pivot points, okay? And it's moving around that. And again, you're not putting the force necessarily on the center of mass, which is what we've been doing so far. You're actually applying the force on some other point that's a certain distance away from the pivot point, okay? All right, so when we talk about torque, okay, so torque is defined as the force required to rotate an object around an axis or a change in angular motion. All right, so you see in the image there a seesaw, right, and again, that would be kind of like the pivot point. It could be kind of there in the center, right, and then this is rotating. No one's going forwards or backwards, but we are kind of rotating around this pivot point, okay, and it causes a change in angular motion, right, and the torque is a force required to rotate the object around that particular axis, okay. So when we talk about calculating torque, right, I mean, it is saying, okay, well, it's a force, but it's not force in terms of just mass times acceleration, right, because we're not actually moving in terms of, speeding up or slowing down in a particular direction. It's more just rotating around something, right? So when we talk about torque, the torque units are actually Newton meters, okay, not just newtons, right? So then you've got, so torque is equal to our perpendicular, which is called the lever arm, okay, we're going to talk about that a little bit more, okay, multiplied by the magnitude of the force being applied to that, to the object that you're trying to get to rotate, okay? So that's what we're doing. Notice here that this is in fact perpendicular, right? So when we're talking about force, or when we're talking about torque, sorry, you have to look at the force being applied to that lever arm in a perpendicular manner, okay? It has to be. So either you're given the force and you have to find what would be the length of the lever arm, right? So the distance from the force kind of to the pivot point to where you're applying the force, that makes it perpendicular to the force, or if you have this distance, you need to make sure you're trying to calculate the force that's perpendicular to that value, okay? They always have to be perpendicular, so we'll be dealing with a little bit of trig here again, okay? Again, looking at that, if you're multiplying this distance, right, it's a perpendicular distance to the force, but meters times your force being measured in newtons, you get Newton meters. Just to, provide that little note, is that it's not a joule, right? A Newton meter is a joule only when the force and the displacement in an object are in the same direction and the force is doing work on an object. But with torque, right, the force and the lever arm are perpendicular, like I was just talking about. So the object is not moving a distance equal, so no object is moving a distance equal to the lever arm, okay? So it's that idea of, you might have seen before, it's like, oh, wait a minute, newtons times meters ends up equaling joules, but that's if the force being applied is in the same direction, like if the object is moving in the same direction that the force is being applied, right, so you're just like pushing something, straight across the floor, then that would work as a joule. But in this case, you're pushing something, but it's causing it to rotate, and the force you're applying, so like if you're pushing down on something and then it's causing it to rotate around, that doesn't count, right? So again, the force has to be perpendicular to the object, right? So in the case of torque, force and the lever arm are perpendicular, so that's why this is not a joule. All right, weird thing. Okay, so one of your most common examples of torque, I gave you one being a door, okay? So with, with a door, yeah, you can kind of consider the hinges as kind of the pivot points. Obviously, it's easier to open a door if you kind of push on the edge, like farthest away, right? Which is why we put doorknobs on the opposite side of the hinge. But another example would be a wrench, right? So a wrench is that tool that allows you to use torque to your advantage, right? Because you're rotating, right? You're taking your force and you're causing something to rotate, right? And you also know that the longer the wrench handle, right? So if you have a longer wrench, or the farther away your hand is away from the pivot point, which is the end of the wrench, right? Where you're attaching it to whatever the object is you're trying to get to turn, right? So let's say a bolt or something, right? The easier it is to use the wrench, right? So if you're just dealing with a really small wrench, you're going to need to apply a lot more force in order to get that object to actually turn, right? So torque must be a factor of both the force applied and the distance from the pivot, right? So again, like going back even to the simpler door example, right? If you, you're pushing on a door farthest away, you need less force in order to open the door, right? However, if you're trying to, again, open the door, you can still achieve that rotational motion if you press, let's say, in the middle of the door. However, you're going to require more force because the distance from the pivot point has gone down, right? So it's kind of equal, it's just, it will change, right? So if you get closer, you need more force. If you're further away, you need less force, okay? Just because of the relationship between them. Okay, so again, where was I with this? So again, yes, so torque's the factor of both the force applied and the distance from the pivot. Torque's often defined as the lever arm multiplied by the magnitude of the force, but again, they have to be perpendicular. Okay, that's the big thing, they have to be perpendicular. The lever arm is the perpendicular distance, right? When we do that calculation of our perpendicular, that's called the lever arm, and it has to be the perpendicular distance between the line along which the force is acting and the pivot point. Okay, so it's like taking the pivot point and going to, drawing that line that's perpendicular to where the force would be being applied, okay? And again, you'll see that in some of our examples, okay? So this would be a good little visual here, right? So this is this distance, right? So this might be, let's say, like let's assume this is like a wrench, right? So this might be a wrench, and this is you're attaching it to like a lug nut or something on a tire, and you're wanting to rotate it, right? So you're applying this force in this kind of direction here, right? This might be the length of the wrench, but that's not necessarily the length of the lever arm, right? The lever arm, value of R perpendicular must be perpendicular to the force that you're applying. So if the force is being applied in this direction, right, and this is our pivot point, we need to now draw a perpendicular line from the force being applied to the pivot, and that will give us our length of our lever arm, okay? So again, you might end up having to use this, length of the wrench and, potentially an angle in order to be able to find that line perpendicular, okay? So that's kind of where we're getting at, okay? So again, there's your formula for torque. The lever arm length measured in meters multiplied by the force applied measured in newtons, giving you a value of torque in newton meters. Okay, so again, just kind of as a note here, if you're going to maximize torque, you need to maximize the length of the lever arm. Okay, that's that value here, right? When the force is applied directly perpendicular to the lever, then the lever arm has reached maximum length. Okay, and that's what's going to give you your maximum torque. Okay, torque is still a vector. Okay, so it does need to have direction as well as that value in newton meters. With torque, though, the only value you're giving in terms of direction is either you're saying it's clockwise or it's counterclockwise, okay? Counterclockwise is assumed as positive, right? So again, you can kind of think of that in terms of mathematical angle properties, right? When you move counterclockwise around the circle in standard position, that counts as positive rotation, and then going clockwise is negative, okay? So in order to determine that direction of torque, right, whether it's clockwise or counterclockwise, it's something called the right-hand rule, right? So again, I'll show you this when we get to do the examples, but what you'll do is you just kind of line your hand up, line your hand up parallel to the lever arm, right? So look where your lever arm is with your kind of index finger on the page, and then rotate your other fingers in the direction of the force, right? So if the force is pulling down or whether the force is kind of pulling up at an angle, rotate your other fingers that way, and then see what's happening with your thumb. If your thumb ends up pointing like up, right? So like turns up out of the page, then that means it's a positive or counterclockwise rotation, right? However, if you end up rotating your fingers to a point like where your thumb ends up pointing down, that would be considered negative or clockwise rotation. Okay, so like I said, torque needs to be measured as either clockwise or counterclockwise, and you can determine that using this right-hand rule. So kind of come back to this to kind of determine that. And again, I'll show you this as we go through some of our examples. So here we go. All right, so in this first one, we have a 12 kilogram uniform beam. Okay, so here's our beam here that has a length of 0.8 meters. So the entire length of this beam is 0.8 meters, and it's mounted on a pivot at one end. So here's our pivot, and it's supported by a cable attached to the other end. Okay, so this beam could potentially move, right? It could potentially rotate, but right now this cable is supporting it. Okay, if the torque exerted, okay, is 298 newton meters, determine the magnitude of force of the supporting cable. All right, so let's get into this. All right, escape. Video. All right, so in that one, again, if we kind of look at our diagram here, just kind of redraw it. Okay, so we have this 0.8 meter beam. This was our pivot point here, right? You kind of see a circle in the other diagram where that kind of represented like the center of mass if we needed it. We had that this was a 35-degree angle, right? And what we were given was that the torque was 298 newton meters, okay? And we were asked about like the, was it the force? I forgot to write that part down. Magnitude of the force of the supporting cable. Okay, so we are looking for the force of this kind of cable that's keeping that up. Right, there's our unknown. Okay, so again, remembering that our force applied, right, so this force of the cable pulling in this direction, it needs to be perpendicular, right, to our, in order to be able to calculate that torque. Right, so what we would need to figure out then is, okay, well, this is the direction of the force. This is our pivot point. Let's draw a line such that from the pivot point to the force being applied, we get a perpendicular distance, right? We get a perpendicular line, and then that will be the length of our lever arm, right? So what we end up getting here is this. And there's our perpendicular. This is the value of our lever arm that we are trying to calculate, okay? So note that here what you get is you get your right triangle, all right, where this would be your hypotenuse of the length of the beam of 0.8 meters, okay? And then there's your angle. So what you're looking for is the opposite side length, right? So that length of your lever arm that's perpendicular to the force is going to be found using sine of that necessary angle of 35 degrees multiplied by their hypotenuse there of 0.8 meters, okay? Once we find that value, which ends up being 0.4589 meters, right, we can then go and take a look at our formula for torque again, which was the torque equaling the length of the lever arm, right, which is perpendicular to force, right, multiplied by that force, right? And we're looking for the force, so we just need to take our torque and divide it by the length of that lever arm. So we're just taking that value of 298 and dividing it by the 0.4589. How much space do I have? A little bit. Okay, so the 298 Newton meters divided by the value there, 0.4589 meters, and we get a value in newtons. Obviously, we get 649.2 newtons, and then if we go back to this, obviously with sig figs, I think we actually only get 2 here, because this was actually given as 80, if we're being honest, right? So this would have to round to 650, right? 650 newtons, or if you like, 6.5 times 10 squared newtons. And again, we already know the direction of that force, right? It's at that angle of 35 degrees as well. Okay, so there's our force on the cable. Okay, all right, let's go back. Okay, so that's the magnitude of the force of the supporting cable. Okay, that's keeping everything put together. All right, and then again, there's your basically the same diagrams ready to go. Okay, so let's take a look at sample problem number 2, right? So in this one, again, you have a cable attached to the shaft of a 395 kilogram crane at a point 4.5 meters from the hinge pivot point. So again, here's your hinged pivot point, right? The cable's been attached 4.5 meters, right, from that length, all right? So the distance from the cable here to the pivot point is 4.5 meters. When the crane is horizontal, so as it is here, the cable will make a 55-degree angle with the crane and pulls on the crane with a force of 1,250 newtons. Okay, so this time we're being given the force that the cable applies to that crane, right? So you can even see in the diagram here, the force is acting at that 55 degrees in that direction there. What torque is the cable exerting on the crane, right? So this time we're actually trying to calculate torque here, okay? And just as a little point of note here, this little point here, this is your center of mass. Okay, so if we were doing this as like a point mass diagram, this is what we'd be concerned with, but not for this part because we're just trying to calculate that idea of torque. So let's do A first, and then we'll go to B next. Okay, so this one, again, here we go. Okay, so diagram again, if we kind of redraw it, right, we had that horizontal, there's our pivot point. This distance was our 4.5 meters. That's where our cable was attached, right? Our force was being applied in that direction at an angle of 55 degrees. We were given that the value of that force was 1,250, not meters, jumping nines, newtons, okay? Okay, so that's the value that we had there. Now again, in order to calculate torque, right, which is what we've been asked, our torque is equal to the distance of the lever arm, which is perpendicular to the force, multiplied by the force. So the force is being applied in this direction, so we need to figure out, well, what's the distance of our lever arm, which has to be perpendicular to the force and attached to the pivot point. So what we're going to get is a distance like this, right? This is going to be our distance of our lever arm, right? So again, you get that right triangle, right, where you have the angle, you're looking for the opposite side length, there's your hypotenuse, so you can set up basic trig and determine that your distance of your lever arm, or the lever arm perpendicular to your force, is going to be found by taking the sine of 55, multiplying it by 4.5 meters. So sine of 55 degrees multiplied by our 4.5 meters, and then that can be multiplied by that force of 1,250 newtons. Okay, so you do all that, multiply it all out, and you get a value of torque of 4,607.75 Newton meters. But again, sig fig wise, we only get 2, so we'll call this 4.6 times 10, 10 cubed Newton meters. And this is where we need to come up with our direction, right? So again, this is either going to be acting clockwise or counterclockwise, okay? So here, again, if what we do is we use that right-hand rule, okay, and we place our thing perpendicular or parallel with the lever arm, and then we rotate our fingers, right, towards the force, right? That way, we end up getting a value that would be counterclockwise, okay, because it would rotate up, right? So we're here, we rotate our fingers that way, right, and we end up getting a counterclockwise. So you can either write counterclockwise, or you'll see places getting like CCW, right, counterclockwise in terms of your direction, okay? Right, so that's, right, placing it there, rotating it that way, your thumb comes up, right? Fingers going that way, so your thumb comes up, so it's counterclockwise. All right, let's look at part B. Dum-de-dum-de-dum. Where are we? Here we go. So part B is saying now the crane is 5.0 meters long and its center of mass is at the center of the crane. What is the torque? What torque is the crane's weight exerting on the crane? Okay, so this one's a little bit different now because we are looking at the weight, right? So now we're talking about like a force pulling it down, right? So force of gravity is kind of coming into play here. So again, if we look back at this now, right? So we're not interested in the cable so much anymore. Instead, what we have is this beam, right? Where this is our center of mass. So force of gravity would be pulling down directly here, right? We know that the length of the beam, the entire beam, is 5.0 meters, right? And again, we're being asked, okay, well, what's the torque acting on the weight, pulling it down? Well, again, same idea, that torque is going to equal our perpendicular multiplied by the force, right? In this case, it's the force of gravity. So again, if this is pulling straight down, what's perpendicular to that? Well, that would be here, right? Because your center of mass was in the center of the crane, as it told us in the question. So that would mean that our distance of our perpendicular is here, which in this case is exactly half, right? Because it was in the center, so half of 5 is going to be 2.5. So our torque value ends up being this 2.5 meters multiplied by your force of gravity, which again is just your mass times 9.81 meters per second squared, right? So that's going to be, they tell you the mass is 395 kilograms multiplied by your 9.81 meters per second squared. Okay, and then multiply all that through. You get a value of 9,687.4 Newton meters. Again, we only get 2 sig figs, so we're going to call that 9.7 times 10 cubed Newton meters. Again, direction of that torque, right, is here. If we put our fingers this way and then we rotate, right, it ends up going down into the page. So what you end up getting there is clockwise, right, or negative. Okay, so again, you might even consider that negative because it's being pulled down, right? So like that force of gravity can be considered negative, multiplied by distance, you get negative, but you can also just consider that as being, rotated down that way. So it's clockwise. Okay, so there you go, example 2. All right, moving on. All right, so again, you see those same solutions there, just kind of type, well, they were from the textbook, so they're just copied and pasted. All right, but those same values of what we were doing. All right, so let's take a look at number 3. So in this one, if a 63 kilogram man were to stand halfway up the ladder that is pictured above, which clearly the ladder has a length of 5 meters and is set up against a wall at an angle of 53 degrees with the floor, determine the torque that the man's weight would exert on the ladder. Okay, so let's go through that one, redraw that picture again. Okay, so in this one, again, we have that the mass of the man is 63 kilograms. We have the following kind of diagram. We know that's the ladder. That's an angle of 53 degrees. Okay, the man is standing halfway up the ladder. So our man is standing here, and since the ladder is 5 meters long, that distance is going to be 2.5 meters. Okay, now we're being asked about, again, the torque that his mass is affecting on, I'm going to reread the question again just to make sure, right? Determine the torque that the man's weight would exert on the ladder. All right, so if we're talking about his weight, right, well, he's going to be being pulled down due to gravity, right? So you've got force of gravity applying straight down, okay? But that force of gravity is certainly not acting perpendicular to this ladder here, right? So again, what we need to consider is this idea of, okay, if we have this parallel value, right, and this is the length that we have, right? So before we kind of adjusted the length with the force that we were given. Now what we're doing is we're adjusting the force so that the force is perpendicular with this length that we have. Okay, so again, what we're looking at here is what is this perpendicular, so the force of gravity is pulling straight down, I want this, right? So I want that value there, the force that's perpendicular to the lever arm, which is here. Okay, so what ends up happening there, right, again, so if that's lever arm, we can consider that being down there as well, right, where you can think of this angle, right, we've done this before with like force at an angle, right, where this 53 degrees in here is the same as this 53 degrees in here, and then what we're looking at is that, again, that, oh my goodness, this value here would end up being like found using law of cosines because it's the adjacent side length and we can find the force of gravity here, okay? So what we would do is figure out, right, there's Fg, okay, which is, you know, we have the mass, so we can do mass times gravity to get Fg, then we can get, multiply that by the cosine of 53 to get your perpendicular force to that, right? So our perpendicular force is going to equal the cosine of 53 degrees multiplied by our Fg, so cos of 53 degrees multiplied by our mass of 63 kilograms multiplied by our gravity of 9.81 meters per second squared. Okay, this is all giving us our force perpendicular. Okay, so we multiply all those values together, we get an answer of 371.94 newtons. Because we're not quite done yet, we'll just keep those sig figs because we've been asked for the torque, right? So now that we have this value, right, our force that's now actually perpendicular with our lever arm, okay, now we can multiply those together to get torque, okay? So we can do that. I'll just kind of make some space up here to do that, right? So our torque, right, so again, like I said, our lever arm and our perpendicular force, right, our force is perpendicular in this case, right, so as long as our lever arm and our force are perpendicular, we can find the torque by multiplying those together. So we can take that 2.5 meters and then multiply it by that value of 371.94 newtons, and we get a value of torque that is 9.3 times 10 squared Newton meters, right? By the time you figure out the sig figs, I think it ends up being like 929.85 Newton meters, and then sig fig with just 2. Okay, and again, this ends up being actually in a clockwise direction, right? Because we're having this, right? And then our force is pulling us down, right? So if we're here, and then our force is kind of hard to see that with my arm, but anyway, you're here, but your force is pulling you down. Okay, so you see that your thumb goes into the page, right? You're rotating your fingers towards the force there. Okay, so your thumb goes down, so that's your clockwise. Okay, so you can call that clockwise or negative. Or again, it's kind of force of gravity pulling it down, so negative also makes sense. Okay, we got one more to look at. Okay, so again, you see that there. Okay, this would be one of those ones where if you were in class, I'd give you some time to see if you could figure this one out on your own. If you want to pause the video and try that, you absolutely can, but I am still going to run through it. Okay, just to give you as many examples as possible, fully worked out, so you can kind of get a handle on what we're dealing with here. Okay, so we have a hinged rod of length 6.7 meters. It's anchored to a wall with a pivot point 4.7 meters from a supporting cable, okay, which is attached at the opposite end of the wall. The cable is exerting a force of 645 newtons on the beam at an angle of 42 degrees. Let's first draw the diagram, right? Let's assume that the wall's on the left, and then we answer the following questions, right? Similar to that one we just did with the crane, we're going to find two things. One, determining the torque exerted on the rod by the cable, and then determining it, now given that the rod has a mass of 7.75 kilograms, determine the torque caused by the rod's weight. Okay, so let's start with that diagram. Okay, so what you've got is that, like, if this is our wall here, okay, you've got this beam that's coming out of the wall. And it said the beam was 6.7 meters, right, in length. I'm going to go back and just reread the questions just to make sure we're doing that right. Okay, so our beam, so our hinge rod, not beam, I guess I should say rod as well. Hinge rod, length of 6.7 meters, is anchored to a wall with a pivot point. So the pivot point is actually 4.7 meters from a supporting cable. Okay, so what we end up getting here is that you actually have this supporting cable that's here, 4.7 meters. Okay, so the entire length of the rod from here to here is 6.7 meters, but you've got this pivot point here at 4.7 meters, and that's where you have this supporting cable that's going to the other end of the wall, right? So it's one end of the wall and the other end of the wall. Okay, and it tells us in the question, okay, the cable's exerting a force of 645 newtons at an angle of 42 degrees. Okay, so we've got 645 newtons being exerted by the cable at an angle of 42 degrees. Okay, so again, our force is this way. We're being asked about the torque, right, from the beam, or from the supporting cable, right? So again, what we need to look at is, well, if this is the direction of our force, we need a distance, like a value of the lever arm that's perpendicular to that force. So, not this value, but this value, right? So that we make that right angle. That's the value I'm looking for right there. Okay, so again, what you've got is setting up this, basic right angle triangle again. This is your 4.7 meters. You're looking for that distance there. That's going to just come from, you're looking for the opposite side length based off of your right triangle, right? So that's opposite. You have your hypotenuse. So it'll be sine of 42 degrees multiplied by your 4.7 meters. Okay, so we multiply those, and we get a value of 3.145 meters, okay, and then we're able to find our torque, because now we have the distance of the lever arm that's now perpendicular to that force, okay, so when we multiply those, right, 3.145 meters multiplied by that force of 645 newtons, right, we end up getting a value of 2,028.5 Newton meters, and we get 2 sig figs there, so really it's just 2.0 times 10 cubed Newton meters, okay? And again, lever arm, rotating force, thumb comes up, so that would be counterclockwise or positive. Right, so counterclockwise there. So that's all the answer for A. For B, you're then asked again about the torque of the crane's weight pulling down. Right, so again going back, right, if the rod or has a mass of 7.75 kilograms, determine the torque caused by the rod's weight. Okay, so let's go and take a look at that. Okay, so we go back to this. Okay, so again, what you've got is the rod here, and the entire length of the rod is 6.7 meters. Okay, its center of mass, right? Not worrying so much about where the pivot point is anymore. We're looking about where's the center of mass, which would be here, meaning that that distance, right, away from where it's attached to the wall, would end up being half of 6.7, which is going to be 3.35 meters, right? And the weight is being pulled straight down by your force of gravity, right? So this already creates a nice little right angle, so that's nice. So to find your torque, right, that lever arm multiplied by your force, which in this case is force of gravity. So this value is your 3.35 multiplied by that force of gravity, which is your mass times your 9.81. They tell us in the question that the mass is 7.75 kilograms multiplied by our 9.81 meters per second squared. So our torque in this case is 254.7 Newton meters. Again, just with the 2 sig figs, so 2.5 times 10 squared Newton meters. And again, if we're thinking direction, right here, force of gravity, right, so lever arm, force going down, right, rotating down that way, and there's your, again, your thumb's going into the page, so clockwise, right, or negative. Okay, so there's all the stuff with torque, right? Biggest thing to remember with torque is that it has to be perpendicular, right? Your force and your lever arm have to be perpendicular in order to accurately calculate torque, okay? So, I mean, sometimes we luck into like these examples where it's just a matter of like, oh, well, the force is acting perpendicular to where the lever arm would be, so great, just a simple multiplication, right? Just maybe trying to find the force. But if once you're starting to bring things in at an angle, think about all your stuff that you know about force at an angle, where you need to kind of create those force parallel versus force perpendicular to a length. Or if you've got the force at a particular angle already, then it's a matter of, okay, well, how do I draw this distance from the pivot point to that force to make that perpendicular to get the correct distance of the lever arm? All right, so it has to be perpendicular, so just kind of keep coming back to that as you're kind of attempting these questions, okay? All right, so there you go, and you've got a couple of questions on a worksheet to try there with torque, and then in a couple days we'll do another lesson focusing more on equilibrium and how we can incorporate what we've learned about torque into equilibrium as well, right? So things about having the torques in both directions being opposite but equal, so you actually don't get any rotation, and that's kind of what's coming up next.